All right, so let's go through this problem just step by step. The first step, we know we have ethoxide. Ethoxide's a pretty good base. We know we've got alpha protons. Doesn't really matter which alpha protons we grab, so I'm just going to pick one side, and then we'll show our enolate down below. And a lot of students at this next step are really tempted to have it react with the methyl iodide in step 2. However, it won't stop here. What do you think could happen? And I gave you the hint. It will attack itself, right? If we think about it, this is 1, 2, 3, 4, 5. So this can form a 5-membered ring, where this enolate will actually attack carbon 5 there and kick up electrons onto oxygen, right? So we're going to get a 5-membered ring. I really like numbering my rings so I can keep track of all my substituents. We know off of carbon 1 we still have that ethyl ester group. And then carbon 2, 3, and 4 are kind of plain at this point. Carbon 5 will have an oxygen with a negative charge. And then an ethoxy group. All right, same thing though, it's not going to stop here. What do you think could happen?
The negative charge jumps down, kicks off.
Yeah, so just like we saw in the Claisen reaction, we can kick off an ethoxide as a leaving group. So we're getting there. So now we've got this double bond, and ethoxide was our leaving group that got kicked off in this reaction. All right, it won't stop here. What will happen next? We have another alpha proton that in this case is even more acidic than our original alpha proton. Why? It's in between two carbonyl groups. So it's doubly resonance stabilized. So we're getting there. All right, so now we've got this enolate down here with the negative charge. Not really much else we can do with it at this point. It'll just stop here. But now we're ready to go with our next step, which is with methyl iodide. Where we can actually alkylate this alpha position. So this is kind of a combo of the Claisen reaction that we saw before and alpha alkylation in step 2. So now we're getting there. All right, at that point, there's not much we can do with methyl iodide. But in the next step, we saw that if you apply acid, what will happen to the ester? It'll become a carboxylic acid, so that's going back to the previous chapter. Okay, so now we're getting closer. However, like we saw the other day, you can actually spin this around. Like this. Let me actually slide this over. So that we get this internal H bonding occurring. You guys remember that? In this case, we've got a decent sized ring system, so that'll occur readily. And then like we saw before, if you apply heat, which was indicated in the reaction, this will steal that hydrogen. This will clamp down, and that will clamp down like that. Let me clean up this arrow. And so we'll do a decarboxylation reaction. At this point, though, we've got our enol floating around. And we know that the enol will quickly tautomerize to our ketone. We know that the ketone form is usually favored unless we have some sort of extended conjugation occurring in the system. I'm not going to show the full arrow pushing for that reaction, though. So what's the name of this product that we made? pain. So what's our longest parent chain? Cyclopentane. So cyclopent would be our parent, right? That's the longest carbon ring. What should our suffix be for this? A known. So the ONE suffix indicates that it's got to be a ketone, right? Yep.
So why isn't this toluene something?
So toluene's aromatic. Is this aromatic? Ah, yeah. All right, so now we need to do the numbering. Where should number 1 go in the ring? The ketone, right? We want that to always be minimized. And then we go 2, 3, 4, 5. So what would this be named? 2-methyl. That's a good point. So we have a stereocenter here. Do we know if it's R or S? No, we don't really have control over making one enantiomer over the other. So likely this is going to be racemic, meaning it won't be optically active, right? We're going to get the S enantiomer as well as the R enantiomer, probably in an equal ratio in this situation. Yeah, does that make sense? So that methyl group coming off could be a wedge or a dash. We just don't know. Yep.
So before you reacted it with the methyl iodide or whatever, wasn't there still technically more alpha protons?
So let's go back and look at Leslie's question. So she was saying, in step 1, we created our enolate, right? And then our enolate, we said, would do that ring closing reaction. And then we could kick off ethoxide pretty quickly as a leaving group. And then at this point, we had this one remaining alpha proton.
So you technically have more alpha protons on the other side?
We do, but that's the most acidic alpha proton that's available.
Okay, so
You're right.
the other alpha protons wouldn't react at all before going on to the next step?
That's a good question. It's not that they won't react at all. It's that this one's orders of magnitude more acidic. So it's going to be plucked off like that, where the alpha protons coming off of this side right there are just not nearly as acidic because they don't get that double resonance stabilization. Yeah. Does that make sense? So this will be the most stable enolate. Really, when you form your enolate, it's going to go after the most acidic alpha proton. And then once you form your enolate, it's going to stop there. It won't go after additional alpha protons, or else your intermediate would have multiple charges, which just is a lot less stable. Yeah, good question, though. All right, so we're going to move on to new chemistry today, and the new chemistry gets complicated fast, so I'm going to try to go somewhat slow with this. It's not that bad. All right, so this is all about conjugation, right? So if you remember back to last term, we said that conjugated systems always have this alternating double single bond thing going on. Let me just say conjugated. And we said that these are really, really different than systems like this, which are isolated. Because we know in an isolated system, you have this sp3 carbon kind of in the middle. Electronically, those pi bonds can't communicate with one another. They're isolated on each end of that molecule. Therefore, they do really different chemistry, right? We saw conjugated systems will do 1,2 and 1,4 addition. So do you remember doing that? Kinetic and thermodynamic control last term. We said that they could also do Diels-Alder chemistry. We're going to see something similar today. So let's compare this to what we've been seeing. All right, so if you remember with our alpha carbonyl chemistry, we can make an alpha beta unsaturated ketone. Do we do that through an aldol condensation or a Claisen reaction? Be an aldol, right? So an aldol is the one where we make the double bond. Claisen reactions where we make 1,3 dicarbonyls, right? So this isn't a 1,3 dicarbonyl. So this would be alpha here, beta over here. So this would be an alpha beta unsaturated ketone. And we could compare this to something like this. This one is not conjugated because it has an sp3 carbon in there. So the one on the right would be considered conjugated. Or sorry, the left. this would be isolated. So even though we're not looking at a carbon-carbon double bond, carbon-oxygen double bonds are still double bonds, right? Even though it's kind of in between a double and a single, it still behaves a lot like a double bond. All right, so now let's think about this in more detail. We know that resonance plays a huge role in these systems. So let's do all the resonance structures for that alpha beta unsaturated ketone. All right, so one's quite obvious. We can just move that pi bond up. Have a positive charge right there. And then the next one, we can move that pi bond over. And we can get 3 major resonance forms here, right? All right, let's think about the hybrid, though. We haven't done this in a while. But with a hybrid, if you remember, I like drawing all of the sigma bonds first. And then we do dash bonds to indicate where there's delocalization, right? So the carbon-oxygen double bond is really in between a double and a single bond. So I'll show that as, whoop, that doesn't look very good, as a bond and a half. Or not even a bond and a half. It's somewhere in between a double and a single bond, right? Same thing with this carbon-carbon bond. And same thing with this one. So we've got delocalization across that entire network there. All right, we know the oxygen in some cases carries a partial negative charge. And then the carbon here is partial positive. And that is also partial positive. So we've got a nice hybrid view here. All right, normally when we look at nucleophilic addition, we say that our nucleophile likes to attack right there. However, in this system, the nucleophile can also attack right there. So conjugated systems have unique reactivity in this case. The nucleophile has an option of either adding to the carbon underneath the oxygen, because that's electrophilic, or that carbon in the beta position, because that's also electrophilic. The reality is it gets a bit complicated knowing which site will be attacked, but I'll try to get you there so that we can predict it with more ease. Does that make sense? All right, so the general guidelines. Are pretty easy to remember. Strong/unstable nucleophiles prefer to attack the carbon immediately underneath. So if we think about a Grignard reagent, for example, we know Grignard reagents are really, really unstable. They'll always attack into that central carbon on an aldehyde or a ketone, without exception. All right. However, stabilized nucleophiles will actually prefer the other carbon. All right, so going back to that analogy, though, we said a Grignard reagent will prefer to attack the carbonyl carbon directly underneath the oxygen. Is there any other sort of reagent that's like a Grignard, but is more gentle? The copper one, right? So the copper reagent, that Gilman reagent, will actually attack the beta position in this situation over that carbonyl carbon. It's a bit odd. So we'll look at this in more detail later on. Yep.
Why?
That's a good question. So the question was why? The main answer to that is we have experimental data saying that that's what happens, right? So this is a theory to back up the experimental data that we're observing. The reality is sometimes it's a bit unclear. We're just making a theory to back up the data. Yeah.
Is it because like that one is more sterically hindered, so you need something more unstable?
So sterics does play a role. Yeah, I would say sterics does play a role, but it's also electronics too. So in organic chemistry, it's always this battle between sterics and electronics. Oftentimes it's not one or the other, it's this combo of both. Yep. Okay, so let's take a look. So let's look at the preparation of these. All right, so this will be a bit of review, but what I want us to do is to figure out what we need to do to make this specific alpha beta unsaturated aldehyde. What starting materials must we need?
Aldol.
So we've got alpha and beta right here. Like I've been trying to drill into everybody's head, is this is the bond that must have been formed, right? So if we break this apart, we know that this must have been one starting material. Okay, so we've got that as one starting material. And then if we think about this other starting material, off the beta position, we also have a hydrogen. What do you think this blue chunk must have been? The same thing, right? So that must have been a CO double bond. All right, how can we push this to form that alpha beta unsaturation product? Heat and what else? NaOH, we need a base, and then heat. If we do the heat, we'll drive this out of equilibrium and actually consistently make this product. So like I was saying before, if you react this with methyl magnesium bromide followed by water, what do you think your product will look like? Predict what your product will be in this spot. And then over here, we'll do a different one. Give me a thumbs up if you think you got the Grignard reaction. That's good. We should all have the Grignard reaction at this point. All right. So if we think about this one, right, the methyl group is going to add in. We'll still have this hydrogen. We'll have this alcohol sticking out here. And then the double bond will be right like that. Does that make sense? All right, let's do the other one. We know that the Gilman reagent, that organocuprate, is a lot less reactive than a Grignard reagent. It's going to prefer that beta carbon. So we'll get our methyl group added right there. All right, so now what I want us to think about is what carbons were added let me back up. I want us to think about what groups were added on to our starting material. So going backwards, we know that this methyl group was added right here. Was there any other atom or element added in? The hydrogen on the alcohol, right? All right, so now if we think about it, this would be position 1, that would be position 2. This would be a 1,2 addition. Does that make sense? If we compare it over here, this would be 1,4 addition. So do you remember back last term where we talked a lot about 1,2 versus 1,4 addition? This is exactly the same thing. So in this case, 1,4 addition is favored with less stable or sorry, more stable nucleophiles. Yep.
I don't get the one part, the one you didn't have.
Yeah, so in this case, let's go back and think about the analogy, right? So do you remember doing this last term?
Yeah.
Where we said last term we could protonate. We would get our resonance stabilized cation. That was position 1. So position 1 is always going to be the far end of your conjugated system, which is analogous to the far end of our conjugated system being right there. It's a little bit different. It's just basically identifying the relative position in which your nucleophile added in. So this would be 1, 2, 3, 4. It's just an arbitrary way of originally numbering your nucleophile, and normally we want to number it so that it's minimized. Yeah.
Didn't share that part last time. That last part of how to number it. Like,
Oh, we did too.
no, you guys, no.
Armand's backing me up. I don't want to pull up my notes, but I'll prove you wrong later. All right. All right. So now let's think about this using some other nucleophiles. The first one I want to talk about is simply referred to as the Michael addition. So we can favor conjugate addition, we said, by having some sort of stabilized or weak nucleophile. So let's write that down. However, in this case, we're going to use a resonance stabilized carbanion. Okay, so let's take a look at what I mean by resonance stabilized carbanion, because that sounds pretty fancy. All right, so let's take a look at this diketone. All right, so we could actually make this using a Claisen reaction, right? Because it's a 1,3 dicarbonyl. If you want an extra challenge, tell me how you would make this. All right, but anyways, maybe I'll put that on the next exam. All right. So we know that these interior alpha protons are going to be a lot more acidic than the alpha protons, like right there, because we know that it'll be doubly resonance stabilized, right? So with hydroxide around, you'll form this highly resonance stabilized enolate. That's what I mean by a stabilized carbanion. So this is resonance stabilized. Which means that this is also a weak nucleophile, and we know that weak nucleophiles tend to favor 1,4 addition or conjugate addition. All right, so now at this point, once we have that made, we can react this with a new reagent. We'll use that reagent that we just made, where we said that alpha is over here, beta is over here. We know that that beta position has strong partial positive character. So this will attack in, kick up electrons all the way to that oxygen. Oops, no double bonds in there. All right, at this point, we've got an enolate, right? So if we think about where our alpha and beta positions are now off of that original molecule, you kind of see how we're tracking them there. I find often students forget about carbons, so if you want to number them or keep track of them using colors, you're welcome to do it that way. But make sure you don't neglect any of your carbons. All right, and then in the next step, we know that this is resonance stabilized. as an enolate. So we can show the resonance structure down here. So we can show our enolate using both forms. But normally you quench these reactions with water. So we can have water donate a proton to that alpha position. To get to our final product. Yep.
So could that emulate attack, or is it just too bulky to it?
So your question was, can the enolate attack?
Yeah, can it attack like our we had before?
So this one?
Yeah.
Right here? Yeah, that's a good question. So this enolate is a lot less stable than the enolate up here. Why? Yeah, it's not as resonance stabilized. So typically at this point it won't continue to react at that beta site. And the question is, well, does it react at the carbonyl carbon? Normally we control stoichiometry so that it won't overreact. So this would be done in a 1-to-1 ratio. Yeah, good questions.
So, but it could.
We will see reactions later where our enolate intermediate can swing around and do chemistry, so forming a new ring. So we'll cover the Robinson annulation later, which is arguably the most complicated reaction we'll see all year. Yep.
Because of the resonance and it's always going back and forth, would we have a mixture of alcohols on that end instead?
Not really. So your question was, can we protonate that? We could. We'd form an enol, but we know that enols quickly tautomerize to ketones. So in this case, it's going to prefer being the ketone, or in this case, the aldehyde. All right. So let's take a look at some common resonance stabilized Michael donors. Yep. These are also known as Michael donors. All right, so some of them are pretty easy to spot. Usually if you have some sort of dicarbonyl in a 1,3 position, it's really easy to make a resonance stabilized group. We saw, one where we could do this also with esters. So whether or not it's a ketone or ester or some sort of hybrid combo. All of these kind of have that similar functionality. All right, there's also some more unique ones. We'll include that underneath. This is a bit different, right? So we don't have a carbonyl on the other side, but we could, if we wanted to, kick these electrons over here and up to nitrogen. So yeah, it does have resonance going in both directions. The other one that's a bit odd but also works are molecules with nitro groups on them. Where do you think the most acidic proton would be on this? It'd be right there, right? Because that's adjacent. Really, it's the only spot with protons too, so that should have given it away. But same idea with this one is we know nitro groups are super strong electron withdrawing groups. So in this case, even though it doesn't have resonance in both directions, it has enough stabilization by the nitro group to make it really, really stable. All right, and then the last one, I've argued with people about this. Some people classify the Gilman reagent as a Michael donor. Some people say, no, it's not a resonance stabilized anything. It's an organometallic reagent. So I'm going to put a little bit of an asterisk here. But really, all of these will do that conjugate addition chemistry. So I like to throw them all in that tub of Michael donors. Make sense? All right, so let's do a little bit of practice. And then I'll have good news for you in a minute. Everyone gets A's, exam canceled. No. It's recorded. That's a legally binding contract. It's on YouTube. All right. So let's do this one. Got LDA. Got this. And that. This will actually give you two products. One will be major and one will be minor. I want you to help me predict what the products would be for this one.
I don't know anything anymore.
Yep. So what's LDA again? Lithium diisopropylamide. It's a super strong, bulky base, right? So let's think about the first step. So first step with LDA, we know that's a strong base. What product will we get after step one? An enolate. We know that the alpha protons are far and away the most acidic protons off of that starting material, so it's just going to stop here at the enolate. It's not going to do any other fancy chemistry. It's just going to hang out here. All right, so now the question is this a resonance stabilized or highly resonance stabilized enolate, or is it just kind of eh? It's kind of eh. So this is relatively unstable. Will this do conjugate addition or regular addition to the carbonyl carbon?
Isolated.
It'll attack the carbonyl carbon, so it's relatively unstable and will favor 1,2 addition. All right, so keeping that in mind, we know at this point that if we have this starting material floating around, it's kind of going to ignore that double bond and just attack straight into that carbonyl carbon. And we would get this as our product. Actually, this should be a negative charge at this point. But then in our last step with our acid, I'm kind of skipping a step there. We would protonate that. To give us this product, right? So this would be our major product. We know that relatively unstable nucleophiles will just do our regular nucleophilic addition. All right. Conversely, oops, we could have it attack at the other site. Where this could attack the beta carbon, kick down electrons up to oxygen. And we know with acid, this will quickly tautomerize from an enol all the way to a ketone. Or I should say aldehyde. I keep on saying ketone. But this would be our minor product. So we do have to always think about what our nucleophile is in these reactions, whether or not it's strong or weak, and then assess which product would be our major and minor product. Does that make sense? All right, so what we're going to do is we're going to stop here simply because we're out of time. The good news is the pod will be due Monday. However, if you want to try getting started on it, you'll be ahead over the weekend.
Wait, is it
Yep.